So thank you again, Tim. And I'm going to introduce our third speaker, Richard Peng. Richard is at Georgia Tech, and he's going to be talking about high-performance linear system solvers with a focus on graph Laplacians. Take it away, Richard. Richard, you are muted.
Can you hear me now?
Yes.
Is the sound quality okay?
Yep.
Okay.
Sounds good.
I can also put on the headset mic, but if you know what, let's just try this.
Is there any difference with this?
That's a little better, yeah.
Okay, all right, I'll stick to this then. Okay, thanks for tuning in, and thanks to the previous two speakers for really emphasizing this connection between graphs and matrices. This talk is slightly different in that I will not be talking as much about how the actual representations of the sparse matrices and graphs are going. I should also say that my own background is more in, I'm coming from theoretical side of things. So my original background was more in graph algorithms. So I'll be looking at some of these things from kind of a more kind of worst case analysis with the kind of the goal of trying to get some kind of provable behavior for some of these things. And then the other difference is that I will be talking about the connection between graphs and matrices at a more numerical level. So the plans, I'll first introduce what is a graph Laplacian and try to really kind of highlight the connection between graphs and matrices. I'll talk about the idea of building graph theoretic preconditioners for this class of matrices. And then if time allows, I'll go a little bit into the numerics towards the end. So the formal definition of a graph Laplacian, Jeremy already talked about the fact that non-zero entries in matrices can correspond to edges in graphs. This is taking it a little one step further in that I will actually let the edge weights in the matrix correspond to non-zeros in the graph. Hold on. I should not be using timings. Okay, I'm going to let the edge weights also correspond to the values of the matrix entries. Specifically, what I'm going to do is I will just put the negation of every edge's weight to the off-diagonal entry, and then I'll put the degree. So the degree of this vertex here is 2, and I'll put it on the diagonal entry. So what this leads to, it leads to a very direct connection between symmetric matrices and undirected graphs. There's also one for directed graphs, but the undirected case is already rich enough to do a lot of very interesting applications. So the funny thing here is I'm dealing with just one kind of matrix, a very specific class of matrices, but I'm kind of taking this theoretical computer science approach of taking one problem and try to really understand what is happening there. So this one class of matrices, it has a lot of direct applications. One reason is that they're related to what's called elliptic systems. So the idea that if you have a spring mass system, so if every edge is just an ideal spring, and then you look at how things get placed, how things get stretched and so on, it lets you do all sorts of useful things like embedding planar graphs. It lets you do things like learning and inference because you can just label some of the vertices to be known labels, and you just let the rest go to the mean energy state, and that gets you to the mean energy state. So that gets you some kind of learned behavior. If you start doing inverse powering, these are actually what's in the spectral clustering type application that Jeremy talked about. So these have been used to do things like clustering image segmentation. From the perspective of graph algorithm, these things are also extremely useful in that if you just set up the linear program and you do take a linear program solver, so things like interior point, second order methods, and you use them to solve Laplacian systems, I mean, what you get out is that you use interior point method to solve the linear program for the graph problem. I mean, this sounds like utterly overkill, but somewhat strangely, this actually gives the current best provable running time bounds. for a lot of graph problems right now. Of course, that's all in worst case analysis, and the worst case analysis kind of picture for solving linear systems is actually kind of embarrassing. In that right now we know very few things that can provably go below quadratic time from the theoretical side. So there are really two different approaches for this. You can do things like matrix multiplication, which take about n to the 2.37 time. And then there's conjugate gradient, which is roughly number of non-zeros times the square root of the condition number. So for both of these, the issue that one get is that there's a fairly large amount of cost to solve these things theoretically. So quadratic time, I mean, so Tim was just saying about a matrix with 1 billion entries, quadratic of 1 billion, that's 10 to the 18, which I think on the largest kind of supercomputers, you can maybe do that in a day or something like that. I'm not exactly sure how fast these things are. Feel free to correct me in chat if I'm severely underestimating how fast computers are now. But the general picture is that it's actually a fairly it's a long-standing open problem of can we get any kind of improvement for a general linear algebraic tool for solving a general classes of linear systems. And on the theoretical side, the picture actually is looking kind of more and more pessimistic over the last couple of years, in that there's a thesis by Peng Zhang who showed that for a lot of classes of structures, especially the ones coming out of 3D finite element simulations, the additional matrix structure often don't help. So the picture there is still kind of murky, but we're getting a lot of very pessimistic results about just solving general classes of linear systems better. And this is kind of the other reason that I would like to focus on graph Laplacians, because on graph Laplacians, it's one of the cases that we now do know how to do much better, both in practice and in theory. In fact, the practical results are actually very much motivated by the very good observed behavior of solving what's called elliptic problems in practice. In fact, when the first theoretical papers on Laplacian solving were submitted, they actually they were essentially rejected with the comment of, hey, you're just solving an elliptic system. We already know how to do that. This is this is a solved problem. Why are you developing new theory for this? In that there are very good tools from scientific computing, things like multi-grid method. They essentially work for any Laplacian systems out there with about 1 billion non-zero entries. Even in MATLAB, if you just call the following command, so the backslash actually runs into some issues, but there is a sequence of magic words that you can say in MATLAB, which is PCG and incomplete Cholesky. This does great for about 10 to the 6 non-zeros. So there is very good evidence that we can solve Laplacians very efficiently. And the reason the works is in this quotation mark is that these algorithms, the problem that these algorithms all run into is that they all rely on this kind of gradual numerical convergence, in that they're not direct or they're not exact solvers anymore. So the way that multigrid or incomplete Cholesky with preconditioned conjugate gradient, the way these things all work is that they gradually converge towards a solution. And it's this gradual convergence that is, to theorists, this is really an interesting phenomenon, because if you stick with combinatorial algorithms, it's actually very hard to set up this kind of behavior. And from a numerical point of view, this is a very common behavior. And this is kind of the behavior that one really would like to understand. So what is this numerical method? The simplest numerical method I know of for solving a linear system is the following. You just do this fixed point iteration. So you just take your x, and every time you just look at the error. So you take ax minus b, you look at what is wrong with that, what is wrong there, and then you just add that to the current x. And the thing to notice about this method is that the fixed point of this iteration, so if you think of both the x on both sides are the same, you have converged. So this is a method that if you set theta small enough, you can kind of imagine that this will eventually converge, except the bounds that one can prove is often terrible for this. So there are some better convergence schemes, but things like conjugate gradient accelerated methods. So these methods were first proposed in the 50s, and then people spent about 20 years getting the better bounds, except they still don't beat direct methods. What made these methods really work is the ability to generate a precondition. So the precondition methods, what they do is instead of just solving ax minus b, you hit it with another matrix B inverse. And the general idea of what a precondition method needs is you want a B that is close to A, but is computationally much less expensive. And this is essentially the observation that made things like conjugate gradient algorithms practical. In that what they want to do is that you can do all sorts of, you can set up all sorts of much less expensive operations. So given an A, you can pick a B to be much easier to solve from an algorithmic cost of perspective, and still get a very good approximation to the point that some kind of iteration gets you good convergence in about something between, say, I think the best I've heard is something like 3 to 5 iterations. The usual numbers I heard is something like 50 to 100 iterations, but 50 to 100 is already a bit on the high end. And the kind of preconditioners, some of them are very simple. Some of them are you just take the diagonal. There's Gauss-Seidel, which is you take the upper triangular part of your matrix. And then there's something called incomplete Cholesky, which is you can just go inside. You can actually go into one of these direct methods. So one thing that Jeremy mentioned is that if you look at the sparse matrix and you look at its cost, this cost is dominated by the need by the creation of new non-zeros. This need of creating B that is closed means that you can actually start dropping a lot of the non-zeros. So you actually go and you just look at the entries, you look at the ones with small value, you just throw them away. And this is actually one of the ways you can start trading between error and the cost of your problem. And the reason PCG iTroll, this is what I was saying earlier about in the MATLAB command, that one works well, is that dropping numerically dropping small entries often doesn't affect the problem so much. And then somehow the outer correction still works for it. So this leads to the idea of generating good preconditioners. And back in the space of graph Laplacians, the reason graph Laplacians became so important is that it's due to this observation by Vaija from about 3 decades ago that say that we can, because the connection between L and graphs are so close, we can use graph theory to build preconditioners. So after about 15 years, this led to the first result that say that we can provably take any graph Laplacian with m non-zeros and solve them in time that is nearly linear to the size. So m poly log n log 1 over epsilon. The Spielman-10 result, which was the first one to get this kind of runtime bound, it received the Gödel Prize in 2015. And it had an astronomically large exponent in this log n to the power of c. But the cool thing about proving runtime bounds is that once you have one runtime bound, it gets you to the understanding where you can prove a much better runtime bound. So after that, in the next about 10 years after that, there was essentially work that halved the value of C roughly every 2 years. And the most recent developments in this space is actually moving away from the kind of the purely graph theoretic method. They're actually looking more and more like matrices methods. So there's this result by Rasmus King. Actually, Rasmus King has a whole thesis on this, which he showed that you can provably get incomplete Cholesky. So there's kind of ways of dropping non-zeros to work. With the slight caveat, the algorithm is still randomized. So there's actually still a lot of work that needs to be done to get that to interact well with the incomplete Cholesky methods and also with the numerics side of things. Especially to do things in a way that you have like good control on the memory management and so on. So that is all very tricky right now. And every time I see Rasmus, I ask him, hey, how is the practical implementations coming? The last I heard is that they are doing very well on 3D grids now, but I think that they are still in the process of getting one of these packages out. So the problem is that because there are all these new applications, the problem I want to talk about is how to compare all these algorithms. So how to get new benchmarks, how to get new ways of comparing all these algorithms, because now you have a huge amount of leeway in building combinatorial preconditioners. So one thing that came out is that because now you can solve any kind of structures, right? So now some of the hard scientific computing instances, things like grids, cubes, graph products, you can even take these Dymax implementation challenges. So Dymax has all these hard graphs coming from things like MaxFlow, interior point methods, shortest path. You can take some of them and you can just set up all the linear systems and you can use them to compare solvers. questions. I can't see the chat. Okay, I'll just continue then. So the way that this kind of comparisons actually started was actually kind of by accident, in that there was this work by Rasmus King, Anup Rao, and Sushant Sakadeva that tried to use one of these fast Laplacian solvers to solve some machine learning tasks. So they were doing some, I think it was some kind of regression problem. And the issue that they ran into was actually they need to rerun the program a couple of times when they use one of these solvers. And they realized some of the solvers, specifically the direct method solvers, so the backslash or incomplete Cholesky, was actually much more numerically friendly compared to some of the other solvers. So some of the ones that's really designed to do images and to deal with grids. So, I mean, we did one of these comparisons on the left. So what it is that on the bottom axis is the linear systems. So every vertical column is actually a linear system. And then we compare the runtime behavior of things like Jacobi, Gauss-Seidel, incomplete LU, MST preconditioner, and algebraic multigrid. And when we compared them, we actually saw some very drastic different behaviors. If you look at the columns, the way that these things are arranged, so the way that the ordering of the 5 solvers also in terms of runtime, this is actually a log scale. They behave very differently as you start going across them. One thing we have realized since then is in the 5 years since this paper came out is actually that this behavior actually heavily depends on which type of interior point method is being implemented, how do you set up the termination conditions, and what kind of numerics do you use in the inside. So this is all a very kind of finicky situation. And what we have essentially looked at over the last couple of years is how to try to take this apart and try to isolate some of these phenomena in ways that one can actually examine the numerical behaviors of these preconditioners. So the preconditioner that we spent the most time looking at was these tree-based preconditioners from Spielman 10 and also dates back to Weijia. So the idea of all these algorithms is that they gradually transform a tree-based solution to a solution on the entire graph. And here there's really 2 kind of different ways of doing this. One is that you gradually pick an off-tree edge, you take the cycle and you solve on it. And the other one is you take a tree, you add a couple of edges, you do a preconditioner. And in both of these algorithms, there's a lot of moving pieces, right? There is how you pick the tree, how do you do a top-down clustering, do you do a bottom-up clustering? How do you set up the numerics? Do you set it to be local? Do you use CG? Do you use accelerated gradient descent? And then furthermore, how do you set up your cache? So do you do some kind of memory layout? Do you do some kind of recursive versus iterative kind of behavior? And it turned out that a very useful, kind of graph to look at was these heavy path graphs. So these graphs are ones where you just make the tree as long as possible to kind of get the numeric behavior to come out as much as possible. So the idea is you pick a Hamiltonian path and you set all the off-tree edge weights so that they essentially have what's called stretch of 1 with respect to the tree. And these are graphs that end up amplifying the difference between the various implementations of combinatorial preconditioners significantly. And they're also the bad case for conjugate gradient, in that these are the cases where if we look at the behavior of there's this one cycle algorithm versus preconditioned conjugate gradient, we can actually, for most of these graphs, things like different stretches, meshes, and so on, we can actually get them to have better behavior than we can actually get some of these combinatorial preconditioners to exhibit significantly better behavior over conjugate gradient. And also, other thing that's interesting is that there is a lot of performance gaps of these various implementations of turning graphs into trees. So because it's a path, right, you can actually set up very optimistic data structures. You can set up this kind of like perfectly separated decompositions of the path, essentially basically a static heap or binary tree representation. And you can start looking at the behavior of how does the performance on that compare to the performance of the whole thing. And to what the performance of kind of the algorithms that use kind of preconditioning, performances that uses some kind of dynamic trees and so on. And what we got this performance diagram shown here, which is that each of the curves, what they are is that they are one of these they're one of these algorithms. And what they measure is that this is the runtime factor. So this is how much slower you are compared to the best performance, which ends up being something that is purely tailored to the path, and to something that's purely tailored towards the path, and this is the fraction of problems to which you are doing significant. So it turned out that for a lot of these, there is a lot of overhead, and for these tree-based preconditioners, one thing that is really not looked at is how to set up or do some kind of predictive kind of analysis to kind of do the graph operations in kind of in a much smoother way, and we believe a lot better could be done for these. The other thing I want to just briefly mention is that then what we did is we started looking at the numerics of these. And here the main funny observation that came out is that there's a lot of numerical issues. And the fact that the preconditioner itself is actually a combinatorial object can actually accentuate some of these issues. And here the most interesting takeaway is how we did this analysis, in that all we did is we took one of these preconditioning algorithms, we put in arbitrary precision floating point numbers. So we took the MPFR package, we hooked it up to it, and then we started measuring the convergence. And what we observed was a significantly better convergence once we increased the amount of precision. Which, if you take this and you kind of take it in the reverse direction, it says that if you just stay in doubles, you're actually running into numerical issues. Your round-off errors actually causing your preconditioners to behave much worse. There were a couple of fixes that we had for this, except I think the more interesting phenomenon is that for a lot of preconditioners, this was even the case. It was actually a bit, so when we talked with numerical analysts, some of them were surprised that this phenomenon can show up. And one thing that is interesting there is whether this is a more general phenomenon or is there any kind of systematic fix to it. So to summarize, the focus on graph Laplacians led us to a much better idea to what are the instances to kind of rigorously test one of these combinatorial plus numerical algorithms. There are some even more recent works on doing some kind of evolving algorithms to evolve the data to evolve data where the performance gaps on these algorithms are actually even worse. The question is, some of the questions I think are very interesting here is, can some of these benchmarks being used for things like incomplete Cholesky? So you take an incomplete Cholesky solver, you put it together with the numerics. Is there a more systematic way to do the numerical kind of behavior analysis that we did? And then the one that I think is very interesting is that can we have other kinds of benchmark measures? So what we did is all we measured against the solver error, right? So we took the solution, we multiplied by the matrix, we look at the 2 norm of the vector difference. A lot of these solvers, they're being used for a lot of other applications. Is there any way we can measure with respect to some kind of ground truth instead of just the residual error of the vectors? Thank you for listening.
Thank you, Richard. Again, we all applaud virtually. And let me again ask if there are any questions for Richard specifically. We have a minute or two. Please raise your virtual hand in the Zoom. At the end, after the last talk, I'm going to invite everybody to just unmute and have a free-for-all. So perhaps that will actually be a better way to do the discussion. Thank you again, Richard. And I'm going to